Hello everyone. Today we're going to be talking about horizontally launched projectiles. Now hopefully you've just watched the Mythbusters video on the bullet dropped versus the bullet fired experiment. If not, I did leave a link of it in the description. Now, I just want to go over the importance of that experiment and how it will play a major role in answering these type of questions. So the idea of that experiment is if you fire something or throw something or launch it horizontally or directly to the side, it doesn't impact how long it takes to fall to the ground. And that's going to be a major principle here and something that we're going to utilize quite a lot. So it doesn't matter if it's fired as fast as a bullet. It doesn't matter if it rolls off a table. It's the same as if it was just being dropped onto the ground. And the main reason for that is it turns out that the things that happen in the horizontal, or what I'll often call as the x direction, if you think of like a graph, and objects that are in the vertical direction, which I often call the y, um, they do not impact each other. So what I mean by that is the speeds do not impact the other axis. So things on the x-axis don't affect things on the y-axis and so on. And that's true for any vector quantity like velocity and acceleration. So let's take a peek at horizontally launched projectiles. So the basics of this notes I'm going to be going over is just one type of question, and hopefully we'll get pretty familiar with how it's done. Now, in order to answer this type of question, we're going to be using a key trick here, just like we use with the vertically launched projectiles. This trick, however, comes in the form of a modified shopping list. So usually we list all the things that we know about a given problem. But this time what I'm going to do is I'm going to do a little bit more than that. I'm not only going to list what they are, but also if they're in the x direction, or the horizontal direction, or the y vertical direction. And to help me keep all this organized, because that's a lot of info, I'm going to be making an XY chart. Now, you can see that I have all the possible variables that I could know in a given problem, VI, VF, A, D, and T. And then I broke it down into my X and Y. And basically what I'm going to go through is each of these to kind of figure out exactly what's going on. So to start off with, we have a ball, rolling at 5 meters per second off a cliff. So it's rolling horizontally. It's going off the cliff. So I'm going to put that in the x direction, the 5 meters per second there. Next up, in the y direction, there is no initial velocity. It's not being thrown down, it's not being thrown up, it's not being thrown at an angle, it's just rolling off the side. There's no initial push in the x or the y, or sorry, in the y direction. Now, obviously, it will gain speed because it's accelerating because of gravity. But for right now, it is just in the y direction is 0. And now this is basically what makes a horizontally launched projectile is that it has no initial speed in the y. So this 0 is going to be true for every horizontal projectile. So if you ever see that word, you know that the initial on the y is 0. Next, I'm going to look at acceleration. Acceleration in the x is also 0, and this is always going to be true for any launch problem. The only way this won't be 0 is if it was somehow being pushed to the right by something like a rocket, or even slowed down to the right by something like a parachute. But we won't be dealing with any type of problem like that, so this will always be 0 over here. In the y side of things, oh, I'm sorry, before I get to that, because there's no acceleration, there's no change in speed, the speed that it rolls off the cliff at, 5 meters per second, is the same that it lands at, 5 meters per second. So I'm just going to keep them both the same. Next, the acceleration is my 9.81 or 10 in the y direction, and that's because gravity's pulling it down. This is also pretty much always going to be true unless it states that we're on a different planet, but we won't be really dealing with that too much. Next is the distances. So I have the 55-meter high cliff. That's going to go on the y side of things. In the x side of things, that's actually what I'm looking for, is how far does the ball travel? I'm looking for the distance in the x. Honestly, the hardest part about these type of questions is filling out this chart, knowing what things are x and y. It takes some time to learn that kind of thing. Now, how these questions all roll is basically the same, and that is the fact that the time is the one thing that bridges the gap between the two. The time in the y is the same in the x. And the reason why is because that time is the time that takes in the air. And it's in the air for as long as it's moving in the y and as long as it's moving in the x. So this is the time in the air, it's the same. The more physicsy way of thinking about it is that the first four of these are vectors, so they have direction, x and y. Time, however, is a scalar, doesn't have a direction. So really there's no such thing as an xy or a y, or sorry, x in the time or a time in the y, there's just time. So I put that equal sign to remind me. And the goals of these questions are pretty much always going to be the same. Figure out the time with the side that you have the most information on. In this case, it's the y side. So I'm going to be using El Grande with these three numbers, and I'm just going to plug them in, the 55, the 1/2, the 10 meters per second squared, the t squared. Now you'll notice that I use a VI of 0. This is the number one mistake when it comes to these, other than, math errors. And that is mixing and matching your x's and y's. You cannot do that. You have to make sure when you use a physics formula that you have only y's or only x's. As soon as you put something like the 5 meters per second from the x and the 10 meters per second squared from the y in a singular equation, you got the problem wrong. You have to make sure you keep these things separate. So after plugging these in, you just need to solve for time. This is just my little step in between, and we get a time of 3.31 seconds when I solve for t. So that's the time in the y, but because there's really no such thing as time in the y, it's also the time in the x, 3.31 seconds. Now from here, the problem's actually really easy. We're looking for distance. We have velocity and time. If something doesn't have acceleration, that means this equation's fair game, our v equals d over t. And from here, you just plug it in. We get 5 meters per second times our 3.31 seconds, and we get 16.55 meters. That's how these problems go. Now, these take a lot of effort to fill out the chart. These are definitely, this is the number one thing. If this is a multi-point question that I'm giving you on like a test or a quiz, most of the points are honestly going to come in from filling out the chart. That is a huge part of this to make sure that you're able to discern between your x's and y's, what things are going horizontally, what things are going vertically. That's pretty much how it goes. So I'm just going to go through this chart one more time in a more general sense so you can kind of look at it for every single problem. In every single problem, the x, the vi, and the vf are always the same. It's the speed that it's moving away horizontally. Now, if it's off of a hill, sure, it's how fast it's rolling. If it's like a gun that's fired horizontally, like in that Mythbusters video, then it would be the speed that it's fired at. It does not change over time. And the reason why it doesn't change over time is because the a is always 0 in the x direction, and that stays the same. D is how far away it goes from the base of the cliff. This is always 0 in the y. So right away, even if it looks like we don't have that many numbers given, like in the last problem I only gave you two numbers, the 5 meters per second and the 55 meter cliff, it may seem like you don't have a lot of numbers, but that's because there's a lot of free numbers. A lot of numbers you know right away. You always know this is 0. You always know this one's 0. VF is how fast it's going when it hits the ground. I find that this one's probably the rarest thing that you have to work with. You don't always need to find it. Sometimes it's given to you and you have to use it, but not always. So just kind of note that there's a good chance you might leave this one blank, like I did in the last problem. Acceleration is 9.81 or 10 meters per second squared on Earth. You can use either one again. If we're on a different planet, then you have to use whatever they give you. Next up, we have how high the cliff is, or how high that the gun is being fired at, or whatever the type of question it is. It's the height of it is really the key word. And finally, the time is how long it's in the air. And again, it's the same in the x and the y. All right, that's everything on horizontally launched projectiles. I know that was a lot pretty fast. The key thing to get these questions right is to simply practice them. Knowing how to fill out the chart is the big battle here, and then simply getting used to the fact that you can only use x things or only use y things in an equation. Once you get kind of those two things down and you get comfortable with it, these problems do become pretty simple. It's just the same 5 equations we've been working with so far. It takes time, it takes practice, but you'll definitely get in no time. I hope everyone has a good day.